Okay. Okay, so we will continue on time reversal symmetry today, and hopefully today we'll finish it, and then next class onwards we'll move on to entanglement and density matrix and all that. Okay, so we proved or we discussed a couple of things last time. One is the general notion of time reversal in quantum mechanics. Okay, so we understood the how time reversal works in various contexts in classical mechanics and electrodynamics, and then we also understood that in quantum mechanics we need something like complex conjugation when we just look at the Schrodinger equation. And then we understood two things last time. We understood the notion of antilinear and more specifically anti-unitary operators, which is generally we understood it because this is a statement from Wigner theorem that we didn't prove but just stated that all symmetries in quantum mechanics has to be represented by either unitary or anti-unitary operator. So this is basically an operation that change one state to another. So notice that what does symmetry mean? Symmetry means an operation that changes one state to another, and such that you cannot recognize the difference between these two states before transformation and after transformation. Now, quantum mechanics has the additional aspect that quantum mechanics is a projective theory, which means it's not just like it's not just the states are represented by rays, which means the interrelation between states matter, not the state themselves. So that gives you a room of or some flexibility that what kind of properties the state vectors or state kets or the operator might hold if they has to be symmetric with respect to any measurement. And by measurement I mean what is relevant in quantum mechanics is the probability of obtaining some value, or what are the eigenvalues that you are getting because of the measurement, or the expectation values. So these are the things that so we demand a symmetry operation is defined as an operation that leaves these things invariant. Okay, and if we want that, if we demand that, then we came across the Wigner's theorem that tells you all symmetry operation has to be represented by unitary or anti-unitary operators that preserves the projection between two state kets modulo a complex conjugation. That doesn't matter because at the end of the day we are going to square it. Okay, that's the probability. Okay, now we understood further that time reversal has the special property that time reversal symmetry anti-commutes with Hamiltonian. Anti-commutes with H if we take theta unitary. Okay, then we understood that if I think time reversal is a symmetry that has to be represented by unitary operator, it ends up anti-commuting with H, and that leads to the physical problem that if an operator anti-commutes with H, that means the energy eigenstate will have a negative counterpart. Every positive eigenstate will have a negative counterpart, which means the system will have a stability problem, right? So this leads to H theta anti-commuting implies every plus E eigenstate with eigenvalue n will have a partner minus E with eigenvalue theta n, right? Which is a stability problem, which leads to a stability problem. So we decided to introduce the notion of anti. So this is already consistent with Wigner's theorem. Then we decided to say theta is anti-unitary, and that leaves us with then if that is true, then H theta commute, and then no such problem appears. Okay, so this is what we learned. And we also did one more theorem which was very simple, that an anti-unitary operator, any anti-unitary operator can be represented at unitary times complex conjugation. So for theta it is just u times k. Okay. And we understand some more subtle points which is about how to use this in the how to apply it when I write a state expanded in some basis states which are eigen states of some operator, how it acts, how it changes only the coefficients to complex conjugation and doesn't change the eigenstates itself. Okay, so this was everything we learned last class. Any points on this? Any question? Any doubt? Local audience, online audience? Okay, very good. So now we will continue on this and learn some basic theorems and properties about time reversal operator, and then further we will we will learn how to represent them for one-dimensional Hilbert space and multi-dimensional Hilbert space. Okay? That will be basically the topic for the syllabus. Okay, so I stated this point last time. Now I'll try to demonstrate it, that if I have an operator expectation value beta a alpha, then it has to be represented by its time reverse partner by alpha theta a, no, not theta, I was representing it using a different notation. I will bring the a later. I was representing it as this Kronecker product, but it's just it is not used here in a Kronecker product sense. If you look at Sakurai, they use this notation, that's why I'm just following it, but this is just a symbol, take it just a symbol. Okay. So this has to be equal to theta alpha theta okay. So let us, this is a very useful identity, which it simply means if someone tells you I gave you an operator, a generic operator, not anti-commuting or anything, some measurable momentum, position, spin, something, right? So this symbol represents a generic such operator, measurable operator. If somebody tells you if I represent the matrix element of this operator as a as a sandwich between two different states, alpha and beta, two generic states, then how will I represent the same operator in these states time reversal partners? So that is the statement. So alpha is theta alpha and beta is theta beta. Okay. If somebody tells you I know this matrix element between these two state states, how will I represent this in the time reversal partners? So this is the prescription. How will you represent this? So let's try to understand this a little more. Now notice it is a bit tricky to explain that how how do I define the action of time reversal operator on the Kate, on the bra and Kate both, right? We have learned how to do it on Kate, but how will you do it on bra? Why it is tricky? Because let us say I have an anti-unitary operator acting on some beta, okay, some generic unitary operator, okay, then I can simply call this, so let me call it some gamma, right? I can simply call this as just gamma, right? Why? Because this gamma and gamma will give you 1, because this is unitary. But you cannot say if theta is anti-unitary, then you cannot say that theta dagger beta is just Kate, is just the opposite dual vector. If this is, so sorry, this is the Kate, this is the bra. You cannot just say that theta dagger beta is just the bra of corresponding to this Kate, right? Because this thing is not 1 anymore. Okay, so that's why it is tricky. So we will avoid defining that, and we will not try to define it, but rather we will work with just the simple form. Okay. Okay, so now let's notice that theta, this theta, capital theta or small theta I just showed here, represents anti-unitary not time reversal, but this one is linear, anti-unitary, anti-linear. This is a regular operator. Okay, this is a regular operator. So now let us define, if I have gamma as,
Sir,
yes,
can you increase the font size a bit?
okay,
And sir, is it possible to switch off the front light? It's like reflecting
oh
and
yeah, sure. Is it very bad for you guys or it's okay? Yeah, sit there. Okay, but it looks
sir,
very dark.
sir,
How
sir,
is it?
sir, the light was better.
Okay, so should we? Is it better?
No, sir, it's better to switch on the light. This
Okay,
way
so
it's
let me
working.
try to open the window. Yeah, can you open that window
Okay, sir.
curtains? Yeah, is this better?
Yes, sir.
Okay. Okay. So now let us try to, so this I can define because this is a linear operator. I can say this is nothing but beta Kronecker product or this direct product symbol. But this is not, for a generic linear operator, I can write this. But I cannot do this, I cannot play this game for an anti-unitary or anti-linear operator, right? That is what I argued. So now let us avoid doing that, avoid defining anything like that and try to prove this statement. So I start with beta alpha, and that is nothing but gamma alpha, because this thing is nothing but gamma, and this is same as alpha gamma. Okay, notice that I have flipped this, so that flip this means there is already a conjugate. Okay, so and this is nothing but, whenever I put tilde, it means it's a time reverse partner. So now I can introduce alpha now gamma tilde is theta times gamma is theta dagger b beta, and gamma tilde is time reversal times this full thing. Okay, now I can introduce I can always do a theta inverse theta. I can do inverse because inverse is by definition identity. Okay, and this is nothing but alpha hence I prove this. Okay, everybody in the same page? Any doubt in any step of this proof? Okay, so now let's see, this is a very powerful
Sir,
yeah,
could you explain the second step?
the second step means this step,
Alpha tilde.
this step.
Yes, sir.
So gamma tilde is gamma is theta dagger beta, right? So gamma is theta dagger beta, but gamma tilde is not theta dagger, sorry, it is this Kronecker dagger beta, but gamma tilde is time reversal times Kronecker dagger beta, right? Do you understand this?
Yes, sir.
Any tilde sign means anywhere tilde means whatever you put in that. Okay, is it clear now? And I used here this. it is by definition 2. It may not be true that theta dagger theta is 1 because it is not unitary, but theta inverse theta has to be 1. That is by definition. Inverse means its identity. Understood, everybody? In the same page? Okay, now let's use this. This is a very useful identity. That's why the proof is important to know. So we are going to use it to understand a bunch of things now. Okay, now some definition. Okay. So if I have a Hermitian observable, that means let's call it A, then beta A alpha is alpha dagger theta A theta inverse beta. Now you can say that now this is a definition. We call this thing could be either plus A or minus A, that we call even or odd under time reversal. Generally all the Hermitian operator are either even or odd under time reversal operation that we know from our classical understanding, right? We know that momentum, position, angular momentum, all of them are either even or odd. These are the only two possibilities. So I define this thing to be plus or minus A. So in other words, so this is the case. So then that implies a certain condition on the phases of this operator matrix element. So let's take that. So beta A alpha is now this thing has to be either plus or minus. So that means this is because of this condition. And you can also rewrite this, put a star, because now I flip the beta and alpha. Okay. So this has to be true. If a operator is either even or odd, this has to be true. So that imposes certain condition, and what are all the possible matrix elements. So particularly this is useful to know the expectation values. Now you are coming close to the physical intuition. So alpha is alpha. If it is odd or even operator, this will be alpha tilde A alpha. Okay. If they are both the same, you don't have to flip them. You don't have to put the star. Right. Now let's do some examples. Let's do some simple examples. Then it will be clear that what is the point of all this exercise. Why did I go through all these complex steps? So let's take the momentum operator. We want momentum is time reversal, is odd under time reversal symmetry. That's what we know from classical mechanics. That means it has to be represented by some operator whose expectation value in time reversal partner will be minus of that, what it was before, right? With respect to the original states. So this must be true. If I calculate momentum in some states, then if I calculate momentum in the time reverse states, it should be related by this. Okay. P is odd, which implies that theta P theta inverse is minus P. That means momentum anti-commutes. Momentum anti-commutes with theta operator. Yeah. Now notice this is not a problem. It was a problem only when it was with Hamiltonian, because that led to a stability problem. Here we don't have a stability problem. Momentum can be negative, not a problem. Hamiltonian is P square. it will be bounded from below because of that. Okay. So now the few more points about the momentum eigenkets. Everybody is in the same page of this exercise and the purpose of this exercise. Online audience?
Yes, sir.
Okay. So one more point, that if you want to construct the partner, which means you want to construct the P tilde. P tilde is simply minus P. So that means basically theta times P is simply minus P. Okay. Now you can do the same thing for X operator. So X, now this is an example I gave you for an operator that is odd under time reversal symmetry. You can do the same for an even operator now. Like position, for example, theta x, theta delta, theta inverse. Okay. So theta x is nothing but x itself. In this case, it was minus b. In this case, this is x itself. Now I leave you this as an exercise. Try to show this, that xipj, okay, acting on some state is expected to give you I h bar delta ij. Okay, so exercise, right? Now show that under time reversal symmetry operation, if you act xipj on a state that is tilde, then this relation remains intact. This relation, the commutation relation, remains intact, which means the interrelation between position and momentum, they don't change, even though the momentum changes under time reversal operation. You understand the point? Okay, let me give a, let's spend a little bit of time here, because this is kind of important. So this is something what we have gone through in several times in many different occasions. That we know that we expect that the interrelation, the physics is basically the interrelation between operator, that will not change under time reversal. Okay, so for example, if it happens that I go to the time reverse partner of time reverse partner states, right? If it happens I go to time reverse partner state, and xipj, this commutation relation, this picks up a minus sign or something else, right? That will change the physics, right? Which means that whatever happens in the forward moving direction is different from whatever, you need completely different way to think about it, right? So that's why this must even though the position and momentum might behave differently under time reversal operation, it's a very non-trivial result. This must remain invariant. Okay, everybody understood the statement? Then I'll tell you a bit how to prove it. Online audience?
Yes, sir.
Okay, so proof is very simple. You just, when you go to the time reverse partner, what you have to do, you have to use the theta here, right? I'm just hinting the proof, you work out the details, right? You have to put this theta here, and so okay, so let's do it like this. So let's start with the regular state, not the time reverse state. Okay, and use theta here. So theta here, okay, and use theta inverse theta here. That is identity, right? So then you are left with theta xi pj theta inverse acting on the tilde IH bar delta IJ, the tilde, right? Now this part is tricky. So that part I leave you as exercise. Not tricky, you can just expand it and see how it works. Now notice Xi behaves like this and P behaves like this. Then how their product remains such that their XP minus XP is invariant. So try to show this. I leave this one step. Okay. Yeah, there is that interrelation must be remain intact. Okay, very good. So that gives you the confidence that that if I have, I don't know if you watch this movie Tenet, that where you have a time reversed world. Okay, it is different. That since that's a movie, they don't do a proper time reversal. Okay, they move some things and some of the other things are not moving. Right, a time reverse world doesn't mean that you just one object is moving and rest of the object are not moving. Everything must be time reverse. So if you go in a time reverse world, if you flip all the time, the sign of time in all your dynamical equation or relation, some objects will be invariant, some objects will change. But your relation between observables, that will remain intact. The form of the physical, the uncertainty and commutation is a very important thing in quantum mechanics, right? That should not change. If that changes, then that means your time reverse partner is different. So that's what we establish, that we our operator, everything is such that it is not going to change. This is also what happened in Maxwell, for example. We saw electric field changes, electric field doesn't change, magnetic field changes, current changes, velocity changes, charge doesn't change, but the Maxwell equations remains invariant. Right? Okay. Okay, now let me tell a little bit about, now let's try to understand what should I do if I'm given an wave function and asked to find the time reverse partner in various scenarios. Okay? What should I do for that? Okay, this part is easy. So first let's prove a theorem that, okay, this is a very useful theorem, but before that let me understand the wave functions. So this is something we already understood from Schrodinger equation, right? But now I want to show it from bracket point of view. So what we understood, that if I have a wave function and I want the time reverse partner of that wave function, I said what I have to do is take a star. Okay. So let us try to understand this from the bracket point of view. That's very simple. That I have a arbitrary state gate, and remember what we did. We can expand it in this position basis. It could be a vector x, it could be 3-dimensional or whatever you need. Now I act theta. How will the theta act? We just discussed this. This was the tricky point. How will the theta act on this side? Conjugate. And what about the x prime? It will remain same, right? That's the basis vector. So okay, and we know this is the wave function. This thing is this psi x. So this tells you that if I go to the time reverse partner, the only thing I need to do is take a star on this. So psi x, actually I should write it psi. I am using psi everywhere. So psi x under TR would go to psi x star. That's all. Now try this exercise. This is a very interesting and instructive one. Let's think of hydrogen atom. There things were a little tricky, right? So the wave function was psi x 3D wave function. It was some normalization okay, and YLM was this thing was e to the power im phi PLM cos theta, right? So how will I take the time reverse partner? So one obvious thing will happen that the m will become minus m for the partner because of this, right? So its partner will have the following effect. So actually it is written like this, L down and theta m theta up. So I take star, right? I have to take star. So that is nothing but, now this is a little tricky that you do by checking the form of Pm. You have to also bring a -1 factor. Okay? This -1 factor, check that why it is coming. Okay. So this is the time reverse partner, of the spherical harmonics, okay? Or this hydrogen atom wave function. The azimuthal quantum number will flip and it will give you an additional phase factor of -1 to the power n. This is a phase factor. This changes nothing. Okay. So this simply means that, so what was the azimuthal quantum number doing? If you calculate the probability current, it was telling you which way this thing is moving, which way this rotation direction is. So when you make it -m, it basically tells you the other way. So you can calculate the probability current from this wave function and show that explicitly. Okay, try this out. This is written in Sakura. It is all worked out. Okay. Now what I'll do, I'll now state a theorem and show you the representation of time. So now we understood the representation of time reversal operator in this kind of systems which has only one scalar, which is only one component wave function. One component wave function. The representation of time reversal is just taking a complex conjugate of the wave function. Okay, we'll see that it is it's little tricky when we'll do it two component wave function or spin half. Okay, everybody in the same page so far? Online audience? Okay, so let me state a theorem and then show you what to do for spin half, and that will conclude this topic. Okay, so theorem. This is a theorem that you have already understood, already have seen. I am just packaging it in a formal tone. That's all. You already know this. The statement is, if a Hamiltonian is time reversal symmetric and eigenkets are non-degenerate, then eigenfunctions must be real. Real with a modulo and arbitrary phase factor. Because we know the example of this. For example, think of particle in a box or harmonic oscillator. The Hamiltonian has no term. The Hamiltonian is what? P square by 2m plus half m omega x square, right? Or some potential. So if you take t2 minus t, that Hamiltonian doesn't change, right? So that means the Hamiltonian time reversal symmetry. And you already know that the wave functions, for example, particle in a box, you can write the wave function as sine n pi l by x. What was this? Sorry, n pi x by l. N pi x by l, u2 by l. Right? It's a real function. It's a real function but you can always multiply it by some arbitrary phase factor that changes nothing. So this is an example
Sir?
of that. Yeah.
Sir, can you please increase the font size?
Okay.
Yeah. What is written inside that bracket?
This bracket.
Yeah, the upper one.
Sorry.
It's a phase factor. Is it arbitrary
Yes.
phase?
Yeah, I was just saying modulo and arbitrary phase factor.
Okay, sir.
Because you can always multiply your wave functions with a phase factor, making it complex, right? So that's why that point is that subtlety is always there. Okay? If I choose to drop that, then it's a purely real function. Now you might wonder that why this theorem is so why it's a trivial thing. We have seen that. So you will not actually appreciate the importance of these theorems now. You will appreciate it much later. For example, my PhD student is doing a problem where he has like 48 parameters in some form in some complex quantum system, and that 48 becomes 24 because he can the system has time reversal symmetry. That means he knows that it must be real, it can be real. Okay, so that means you need only one number to represent one of that. You don't need two. It's not a complex one, right? So these kind of things will become very handy when you do various complicated problems. Okay, and that's why this you may not appreciate why I'm doing it now, because it's a trivial thing you already know, but it turns out that those theorems are kind of guiding light for very complicated problems which you don't know how to navigate. Okay. Okay, so now let's prove this theorem. It's very simple. So if it has time reversal symmetry, it means the theta operator commutes because it's anti-unitary that we established. So H theta n is theta H n, and that is T n theta n. That means, of course, this is true. That means if n has an eigenket n, if an eigenket n has eigenvalue en, that means the theta n will be an eigenket also with eigenvalue en. But I said it is non-degenerate, which means theta n must be some phase times n. Okay. So that means what? That means if I write the wave function form x prime n and x prime theta n, so if I write this, then this one must be. Now these two are same, and I got rid of this modulo factor because I said I don't want this factor. So that means x prime n must be equal to x prime n star. Okay. That means if something is equal to its own conjugate, that means it's a real function. Okay, that's the only possibility. Okay, this is the theorem, and it might appear trivial because you have seen it many times, but that is just that. Okay. Everybody is in the same page. Okay, now try this. This is also I am telling you one more result, which I want you to try to internalize and understand. So I said earlier that if I want to go to the complex conjugate, I want to write down the wave function that is time reversal symmetric transfer after time reversal symmetric of a wave function. Then all I have to do, I take psi x to psi x star. Okay. Now what will you do if you have a wave function in momentum space? What you have to do is this, and that's very easy to see. All you have to do is this. So alpha is just the same token as before. Alpha is p prime alpha. So theta is, so this is star and this becomes minus p. because theta acting on P will give you minus P, theta acting on X will give you X. Now you can exchange these two because they are symmetric. So dt is P prime. Actually, I should use psi again. That just tells you this. Okay, same basis, you just have to take the P2 minus. Okay, now I will conclude this chapter. Now I learned what is the representation of this symmetry for one component wave function. Okay, so now let's try to see what happens to angular momentum. Angular momentum means we want to now go towards spin half or spin in general. Okay. So what do you expect for this? Is it odd or even? J is angular momentum. Odd, right? Because it's x cross p in classical sense. Okay. So now if I think that spin is an angular momentum and I look at the representation of spin operators, let us just first notice one thing. Let me just put it in a box. 1D representation of time reversal. Okay. 1D representation was so theta acting on psi will give me e to the power I theta k. Right? K will just take complex conjugate, whatever is there. That's what we just did. Psi expressed in terms of x and all. Right? And this I theta means I have a freedom of keeping an arbitrary phase factor. If you go to Sakurai, they write this thing as eta, but I can just write it as e to the power I theta. But notice that the theta square must be equal to identity, right? Time reverse of reverse will come back. This thing is going to screw up here. That is very interesting. We'll see how. So why? So I'll tell you in a moment why. But let's just say go through this. So this is theta square psi is theta times e to the power I theta k psi, right? And this acting on this is doing k twice. That means you are again back. Doing complex conjugation twice means nothing. And you can write this theta as theta dagger theta. So then this e to the power minus theta cancels and you are back to psi. Okay. Okay. So this is the 1D representation of time reversal symmetry. It is nothing but complex conjugation. That's what we already established. I am just writing it in a compact form. Now what to do when I want higher dimensional representation? 1D means it's one component. Higher dimensional means you have two components, three components, spin half, spin one, that kind of a function. So what to do there? So let's start with the simple case and then I'll make a general statement and I will ask you to look at the proof of that, but I'll prove that statement for spin half and one. Okay, so what do I expect? Each of these components should be behaving in the same way. Right? So we expect all the spin operators to flip sign under time reversal symmetry. Right? Now we know that theta is some u times k. So we want to find what is that u, because I know there is a k. What is k? We know it's complex conjugation. We don't know what is the u. So let's apply K on this. So K acting on sigma x in spin half. So K inverse is basically just an applying K is sigma x. Right? Only this one changes sign. These two just, everybody knows that why, right? Online audience? You know that?
Yes, sir.
Okay. It's a Z basis representation, by the way. It will not be true if I am not in the Z basis. Because in SZ basis, sigma Z is diagonal, sigma X is, I am leaving the H bar. This is the only one complex. So that's why when you take complex conjugate, it will flip sign. So that means my U could be simply this. So I demand the following. The U should do this. U sigma X U must make it sigma X. U sigma Y U sigma Y. U sigma Z U minus sigma Z. So what could be a U which does this job? Which U will do that? A sigma y, right? A sigma y will do that. So I can take the u as sigma y, right? Because sigma y and sigma x will give me minus sigma x. Sigma y, sigma y, sigma y will give me sigma y. Because 2 sigma y will give identity. And
Sir,
sigma y, sigma z, sigma y will give me minus sigma z. Yes.
sir, where you have written that with the help of this time reversal operator, theta sigma x, theta inverse equal to minus sigma x.
Yes.
Like how do we know that? Like for angular momentum, it's obvious.
Yeah. Because sigma is an angular momentum, right? It's the x component of angular momentum.
But like it is related to spin, right?
Yeah, but don't we have not we seen that how it couples with the magnetic field and all that? Like we have seen that if I uh, put a spin in a magnetic field, right? Then the Hamiltonian you get, you treat the spin like a angular momentum, right? So spin is an angular momentum, right? The representation of spin is an angular momentum. The spin generates an angular momentum. Isn't that true?
Yes, sir.
Yeah. So are you confused that why spin is an angular momentum?
No, sir. No, sir. I thought like
Okay.
in case of angular momentum, we know that this is true, but I thought like there is something else related to
No,
this.
no, no. Spin is an angular momentum, right?
Yes, sir. Yes. Okay. Sir.
Yeah. Everybody else are clear about this point? Why spin, angular momentum, and all that? Okay. So now I can represent my operator as, so theta is e to the power I5 sigma y. Okay. Sigma y times k also. Actually, yeah, sigma y k. Okay. Now normally this phi is chosen to be pi by 2 to make this whole thing real, right? So what you write is u is I sigma y, because if it is pi by 2, this is just I, and this you get 0 1 minus 1 0. So normally your tau is I sigma y k. So this is the two-dimensional representation of time reversal operator. Okay. Now comes the peculiarity. This is doing this job perfectly, but this will screw up something else. Okay. Can somebody guess that what is going to screw up? What do we want? We want theta square to be identity, right? But this is not. Because if you take theta square for this particular theta, you will get minus identity. Okay? Because sigma square is 1, kk is 1, I square is minus 1. So now you are running into this problem. Yeah. So you can just write it as, so this is basically I sigma yk, I sigma yk, this is theta square, this is I this is just minus 1. So it's projective representation up to a sign. So this is the problem of spin half. Now this is a general, yes, yeah.
Sir, for that u sigma x u, like how are we writing that it would be minus sigma x?
Sorry,
For where we have mentioned that u sigma x u equal to minus sigma x. How are we
u
writing that
sigma x.
minus sign there?
Sorry,
The last
this
line.
one
The last line of the left side. Left
here,
side. Sir, left.
here,
Yeah, down.
yes,
Yes, sir, that.
yes.
So how are we mentioning that u sigma y u will be plus of sigma y?
This,
Yes, sir.
because of this, the k will give a minus sign. So the u cannot give a minus sign, and I want this, right? K already brought the minus sign, right?
Okay,
Do you
sir.
understand? I want a representation. I am constructing a representation of theta that will give me this, and I know the k is already giving me minus sign, which means I should choose my u such that it doesn't change the sigma y. And the simplest representation is this. By the way, you can be flexible about this. You can choose something else, but this is the simplest representation of sigma uh, of theta operator for a two-dimensional Hilbert space. Okay.
Okay, sir.
Okay. So now this is a general statement, so which I am not proving, but I want you to think about this. So theta square acting on j or s, whatever you like to say, half integer will give you minus j half integer. I just showed you for spin half, but this is generally true. The proof is little inward. Theta square acting on j integer will give you okay. Now this is generally true, and you will find sometimes people are representing this theta as this form. So instead of I sigma y, you will find them representing in a more general form, which is also same. So theta is represented as eta. Eta is basically the arbitrary phase factor. Eta times e to the power minus I pi sigma y or jy, in general jy by h bar 2. You can put sigma y and you will see this is the same thing. This becomes the same thing. The matrix form becomes the same. Okay. Okay. So I'm just writing things for spin half. I just showed you for spin half, but this is generally true. Now this, you might wonder that what does that mean? What does it all that mean? So it means that spin half has these peculiar characteristics which you have seen earlier also in rotation. It says that it doesn't return to itself after 360-degree rotation. Right? It doesn't return to itself after 360 rotation means if you have to do a 720-degree rotation to come back to a spin half. Right? That's we have seen this hand and cup example for a classical spine. So this also has this peculiar property under time reversal that tells you if you time reverse it twice, it picks up a minus sign. It doesn't return to itself. Okay? You have to do it twice more to come back to itself. Okay? So this is the interesting property of spin half or half integer objects. Now why it is so, that is actually a very interesting discussion, and that I will not try to touch on this course, but you are there are ways to think about this problem using Berry phase of spin half and all that. Okay, so that I will not get into in that. But just notice that spin half has this interesting property, and that leads to another interesting, that has an interesting consequence. The consequence is following. So it tells you that okay, I will just state this statement, that this implies that spin half systems or spin half integer, or not spin, just total angular momentum. It could be combination of spin and orbital. Angular momentum half integer systems has, so let me write it separately because it's an important statement. Time is up, so I'll just write the statement.
Sir,
Yeah.
sir, this theta square means we are operating the theta twice, right?
Yes.
So aren't we going to the same direction itself after translation, like twice?
No, if I apply theta on a, so for example, let's say do theta on p, you get minus p, right? Then do theta square on p, that means theta of p and theta, that means theta minus p, that means p, right? This is the simple expectation.
Yes,
So
sir.
it is negative of negative, which means it should be positive.
But in the case of this spin half, the sigma y, we are
Yes.
getting like -1. So
Yes.
so
No, that means in this case, if you go twice, if you time reverse twice, you won't return into that. This is peculiar, and this you cannot match in intuition. But this is the peculiar property of spin half. It is peculiar in the same way that you cannot make sense that I cannot do it like the way I have gave the example of 720-degree rotation. There is no classical counterpart of this. This is a purely quantum phenomena. Okay.
so is there any explanation behind it?
Yeah, that's what I said. You can explain it when you represent this. Think about the Berry phase of this system, but that's little tricky. That's little complicated.
Okay, sir.
So that for that you have to learn. Yeah, so that's tricky actually. You have to learn something more. So I can give you some references.
Okay, sir.
But
Thank you.
the main point is spin half integer objects have very strange properties, in terms of time reversal and rotation. Now the rotation you can still explain using it as a multi-component wave function, but time reversal one you cannot explain like that.
Okay, sir.
Actually, let me think. I am not sure about this. If I take a two-component classical object, yeah, I'm not sure, but I think you cannot explain it from a classical point of view. So if I take a two-component classical object, can I do a motion reversal and land on some negative state? I don't think so. It's a purely quantum property. So if you want to so let me tell you how we landed on this. At least we landed on this by demanding to satisfy this. The property of angular momentum, right? And then we said, what we showed, that if I want to find a theta operator that does this job, then that theta operator must be theta square for spin half. We showed it for spin half, but it can be proved for any spin half integer. Okay. Now we already have seen for spin 0, spinless object, that problem doesn't happen. Spin 1 I didn't show you, but you can try to do this for spin 1. So try to construct the theta for spin 1. You will discover that this theta squared will become itself. So this is how we landed on this. So there is no way to construct an operator, okay, that satisfy both this and this. For half integer spin. Okay. Now, what does that mean? What is the physical meaning of that? It simply means spin halves are weird. Okay, they don't come back to itself after twice reversal. But why are they so weird? Okay? That requires you to understand it from this very phase point of view, and then there are other ways to think about this. So you can think that a spin half is generating some magnetic field, right? So you can think it in terms of that. It's generating some kind of magnetic field, and that magnetic field is breaking time reversal symmetry in this weird way. Okay? That is another way of thinking about this. Now, why spin half's magnetic field is that weird, but not spin integer's magnetic field is not that weird? That requires some non-trivial discussion. You understood the point? Did you understood the premise?
Yes, sir.
I didn't give you an answer why, but I gave you as much as possible around the why. Okay. Okay.
Yes, sir. Yes.
Okay. Now let me make this important statement, which I will not prove, that for half integers spin, there is a degeneracy, which means if I have a state n, then the state theta n, both of them satisfy this. Okay, that you can prove using this point, that for half integer you have theta square is -1, so you can show that this theta n is different from n. It has to be different from n. Okay? So these two, the important thing is n and theta n, they are different states. So try to see the proof is there in Sakura. They are different states. That is the important point. That is the what you have to prove. Okay. If something is half integer spin, TRS. So TRS means H theta commutes, right? If H theta commutes, then this is definitely true, right? But that doesn't mean these two states are different. Right? So that is what you have to show. To show that these two states are different, you have to use this fact. Okay? That is where this statement is true only for half integer spin. For integer spin, they are not different. Okay? So this thing is called Cramer's degeneracy. So this theorem is called Cramer's theorem, which showed that this degeneracy will be there always. And it's a very powerful theorem. It helps to identify many important property of many exotic systems like topological insulators and all that, where you look for Cramer degenerate points and can confirm whether it has this certain kind of invariance and all that. Okay. So that is what completes this. Okay. So definitely do this proof. I am not doing it in class means I can ask it in exam. Okay. So definitely do this proof. Very easy. It's all worked out, and the only difference from all the proofs we have done so far is the fact that this n and theta n are different, and that you can show by using theta square equal to -1. That's the only thing. Okay, that's all. That completes the chapter. Okay, on this time reversal symmetry. From next class, we will start on entanglement and density matrix. Okay, if there is question, you can ask now. Okay, that's all. Spin halves are very peculiar object. As you will learn more, you will see. And you will see more and more that they are intrinsically quantum. There is no classical counterpart of it.